Hello everyone. In this session, we will discuss chapter number 3, electrical machines. Before discussing electrical machines, let's have a brief review of magnetic materials. Magnetic materials are the materials which are used to prepare a core in electrical machines. The electrical machines could be static machines like transformer and rotating machines like motor and generators. So in every electrical machine, the magnetic materials are very important component. Now, whenever there is a magnetic material, there will be a magnetic field. And magnetic field is nothing but it is a force generated because of energy change in a volume of space within the material. This magnetic field is generated or produced by an electrical charge in motion. Electrical charge in motion means electrons in motion. For example, when current flows through a conductor or orbital movement and spin movement of electrons around the atom nucleus. The magnetic field can be described by imaginary lines as shown in the diagram. We cannot see these imaginary lines, but it can be experienced. So in this diagram, first diagram, there is a permanent magnet having two poles north and south, and we can see from the diagram that the magnetic field lines are generated or started from north pole and they are terminated to south pole. In the second diagram, there is a coil or winding which is connected across the source, DC source, and when current flows through the winding, an EMF is generated, a magnetic field is generated around the coil. So the first diagram, it is a permanent magnet which is having a magnetic field or magnetism around the magnet. In the second case, the magnetism exists, magnetic field is generated only when the current flows through the winding. In a permanent magnet, there are orbital motions and spins of electrons within the permanent magnetic material. And these two types of motions, orbital motion and spins of electron, lead to a magnetization within the magnetic material, and around the magnetic material there is a magnetic field. So in natural condition, this magnetic material or permanent magnetic materials, they will generate a magnetic field around it. So this is a horseshoe magnet, and one part, one pole is, let's say this is north and this is south. Here two bar permanent magnets are shown, and we can see magnetic field lines are started from north pole and terminated to south pole. This is magnet 1 and magnet 2. Both the magnets are placed near to each other. So from magnet number 1, north pole, magnetic field lines are started and terminated to nearby south pole of the magnet number 2. In a permanent magnet, there is a limitation or disadvantage. And the disadvantage is here magnetic field of this type of permanent magnet cannot be changed. For example, once the magnet is manufactured, its magnetic field strength or magnetic flux is constant. With respect to time, its magnetism is decreased, but we cannot increase or we cannot change instantaneously the magnetic field. And this is the disadvantage of permanent magnet. In many applications, we need a controllable magnetic field. Sometimes we need higher field, sometimes we need less amount of field. So we need to control the magnetic field. And an electromagnet which provides, which gives the controllable magnetic field. In this type of magnet, the magnetism exists only when current flows through the coil or winding, and this coil or winding is placed on a magnetic material which is known as a core. So for example, there is a core like this, and over the core winding is provided, and this winding is connected with the source. Now this source could be variable source, or in series with the source a variable resistor is provided. So by controlling the resistance, we can increase or decrease the current flowing through this winding, and depending upon the magnitude of the current, the magnetic flux around the electromagnet is controlled. So in this circuit simple schematic arrangement, you can see there is a simple resistor connected across a source with the help of switch. With this circuit, one compass is placed. When the switch is open, the current is zero, and in the absence of current, there is no magnetic field. As a result, this needle of the compass is pointed towards the north pole of the earth. But when we close the switch, current I is set up through the circuit, through the conductor, and around this conductor, magnetic field is generated. This magnetic field is stronger than the north pole magnetism, and as a result, the needle of this compass is attracted toward artificially created magnetic field. In this case, the source is DC, and this arrangement is called an electromagnet. Now here this resistance is a fixed resistance or fixed resistor. If we provide a variable resistor, by increasing or decreasing the resistance, we can play with the current, and depending upon the magnitude of the current, magnetic field or magnetic flux can be controlled. The same thing is shown here. There is a core. So this cylindrical part is a core which is made up of good magnetic material. Over this core, there is a winding having n number of turns, and this winding is connected with source, switch, and variable resistor. And as I said earlier, changing the value of resistance, we can increase or decrease the current flowing through the winding, and it will decide how much amount of controllable magnetic field is generated. In this case, if we change the terminals of the supply or battery, for example, at present this left hand terminal is positive and right hand terminal is negative. But if we change the terminal like this, reverse the terminals, then the poles can also be changed. For example, if this is S and this is N with this original connection, and if we change the terminals, if we reverse the terminals, then this part becomes north pole and this side becomes south pole. So this is advantage. Advantage is we can have a controllable magnetic field. Controllable magnetic field. Not only controllable magnetic field, but by changing the direction, or by changing the direction of current, or by changing the terminals of the source, we can also reverse the poles. So south could be north and north could be south, and so on. And this is very important advantage of electromagnet. Whenever there is a magnetic material, that material has one important characteristic, and that characteristic is known as BH characteristic. It is also known as hysteresis curve. This is also known as hysteresis loop or hysteresis curve. So this is BH characteristic. Let's see what is BH characteristic. BH characteristic, we have to understand two terms. One is magnetic field strength or magnetic field intensity. Whenever a magnetomotive force or MMF is there. It is the ability to create a magnetic flux in any magnetic circuit. Magnetic circuit means core and winding. So whenever there is a core, there is a winding, and this arrangement is connected with DC source, there is a magnetomotive force. And the magnetomotive force will generate a magnetic flux in that magnetic circuit. So in this diagram you can see there is a ring type or toroid type magnetic core. Over this core, a winding is provided with n number of turns and it is connected with a source. So current is flowing through the winding, and when current flows through the winding, it will generate a magnetic flux phi. Now this magnetic core has a cross-sectional area A meter square, for example, and the mean length is L meter. So using these physical dimensions, we can calculate flux per area, that is flux phi divided by area of this ring core. And if we calculate flux per area, it is nothing but magnetic flux density B. So B is given by flux divided by area. And what is the unit? Unit of flux is Weber and unit of area is meter square. So the unit of flux density B is Weber per meter square. Now for this circuit, a few important terms are written here. One is MMF, magnetomotive force. It is given by N into I, product of number of turns and current. Its unit is ampere turn, AT. Another term is H. H is magnetizing force and it is given by MMF divided by length. So Ni upon L, ampere turn divided by length. Length is in meter, so ampere turn per meter. B, as I said earlier, flux density, Weber per meter square, and B and H, they are related with mu. So B is equal to mu H, where the mu is permeability of the material and mu is given as mu is equal to mu 0 mu r. So B, we can write B is equal to mu 0 mu r into H. Now this H is called magnetic field intensity or magnetic field strength. It is also known as magnetizing force. This is measured in ampere turn per meter and its mathematical equation is H is equal to Ni upon L, that is magnetomotive force divided by length of the magnetic core, AT per. Now what is BH curve? So you have to remember that 3-4 relations: equation of B, equation of H, and the relation between B and H, that is B is equal to mu H. Now for any magnetic material, this mu is constant, almost constant, if we do not change the operating conditions. So we can write B is directly proportional to H. And what is the equation of H? H is equal to Ni upon L. Now in this equation, Ni upon L, N is number of turns and L is length of the magnetic circuit, and both are constant. Both are constant. So we can write H is proportional to current I. If we club all these relations, then B is proportional to H and H is proportional to I. This is sequence. So whenever we apply current through any magnetic circuit, for example, let's say there is a magnetic circuit and we are applying the current I because of the source, then this current will first generate magnetizing force H near the circuit, and because of this magnetizing force H, the magnetic flux density or magnetic flux density B is generated. So what is the hierarchy? First, there is a current in the circuit. Current will set up magnetizing force, and magnetizing force will set up magnetic flux, and from magnetic flux we can calculate magnetic flux density. So what is BH curve? BH curve is graph, or it is a plot between flux density B and magnetizing force H. It is a graph, it is a plot of B versus H. For non-magnetic materials, non-magnetic materials are the materials having very small value of relative permeability, around 1 or less than 1, like air, wood, paper, etc. For non-magnetic material, BH curve is a straight line because the mu value is 1. So when you say B is equal to mu H, mu value is 1, so B is equal to nearly H. So the graph between B and H is a straight line. But for a magnetic material, the value of mu is considerable. It is greater than so many times greater than 1, and because of that BH graph or BH plot is not a straight line, but it is a curve. So here you can see a BH curve. B is taken on y-axis and H is taken on x-axis. For non-magnetic material, BH graph is a straight line, but for magnetic materials where mu value is considerable, then BH curve is curve. The graph is not a linear line or straight line but curve. So three examples are shown: sheet steel, cast steel and cast iron. Depending upon value of mu, the curve is this. Now magnetic flux density already discussed, so I am not repeating. B is equal to phi upon A Weber per meter square, and it is also measured and in Tesla. So let's see what is BH characteristic. How can we plot the BH characteristic? Here you can see very simple circuit. There is a core. The cylindrical part is a magnetic core. Here it is written. The core consists of n number of turns, a winding having n number of turns. It is connected across a DC source having voltage V in series with a variable resistor. Due to this source, current I is flowing through the circuit, and if the value of resistance is very high, current is very low. So let's assume at present we set the resistance very high so that current is negligible. When the current is negligible, H is negligible and B is also negligible because B proportional to H and H proportional to I. When we reduce the resistance, the current will be increased, and this will increase H, H will increase B. So here when we decrease the R, when we reduce the R, it will increase the current, and increased current will increase H. This increased H will increase B. So this is a sequence. With the reduction of resistance, current is increased. With the rise of current, H is increased because H is equal to Ni upon L. And when H is increased, B will be increased because B is equal to mu H. So with the increase in current, H and B both will be increased. Initially, B is increased linearly. with the increment of H and I. And gradually as H is increased and it reaches up to certain value, the rise of B is reduced or slower down. So what is the condition? Condition is initially B increases linearly with H. After reaching some value, the rate of rise of magnetic flux density B is reduced as the magnetic core, most probably it is iron, the magnetic core starts to attain magnetic saturation. So after reaching some value, it depends on type of the core and value of permeability, the rise of B is reduced. Now the rise of B is not linear, but it will be increasing in a particular way. So that I will show you in the next diagram. With the increase of H, the increase of B, now it will be non-linear as shown in the figure, and in the diagram this portion is shown by part AB. So let me show you the diagram. So starting from A, initially when the current is 0, the B and H both are 0. When we reduce the resistance, current starts increasing. This will increase H and H will generate B. So we will get this type of curve. So initially up to, let's say up to this point, this graph is linear, and after this point the graph is curve. So this AB portion is a graph of B versus H when we reduce the resistance and increase the current. After reaching point B, this point B is known as a positive saturation. A positive saturation means the value of B becomes a maximum. So this is written as Bm. Bm means B max. After reaching this point of H, if we still increase current, H will be increased, but B will not be increased because it enters into saturation region. So even if current is increased, H is increased, the B will not be increased and the graph becomes like this. So this point B is called a positive saturation. Once the graph reaches to positive saturation or magnetic flux density becomes Bmax plus Bmax or positive Bmax, let's reduce the current by increasing resistance. So if we increase the resistance, current starts decreasing. If current starts decreasing, recall the equation H is equal to Ni upon L. If current starts reducing, H also starts reducing. And as a result, B is equal to mu H. So as H is reducing, B also starts reducing. But now, this reduction of magnetic flux density will not follow the earlier graph. Earlier graph is AB part or AB path. So when we reduce the current, now B and H graph will not follow the original path AB, but it will follow a completely another path. For example, this. So from B to C, magnetic flux density starts decreasing and it will follow BC path. So during AB, B is increased and on BC path, B is reduced. Now what happens at part C? You can see at point C, H value is 0. So current is 0, and when current is 0, H is 0. Even if H is 0, B is not 0. B is having this much value, this much amount of magnetic flux density is there. This is known as remanence, and this much amount of magnetic flux density or magnetism or magnetic flux is known as a residual magnetism, positive residual magnetism. So the condition is current is 0, H is 0, but flux and flux density are not 0. They are having a small value, and this property of any magnetic material to store the magnetic flux even if current and H value are 0 is known as retentivity. This is called retentivity. Retentivity because the magnetic core has a retention of magnetic flux even if current is 0. So now what to do to make magnetic flux 0? To make the magnetic flux 0, we have to supply the current in opposite direction. So in earlier case, this was the circuit winding and current source is connected like this. Let's say this is A and this is B. A is positive, B is negative. So to make this magnetic flux density completely 0, we have to reverse the flow of current. So earlier current was flowing in this direction. Now we have to change the direction of current like this. And for that, we need to change the terminals of the source. So from B negative, now we have to convert this part positive and this part a negative. So by changing the terminals of the source, we will reverse the direction of current, and as a result current starts flowing in opposite direction. Now when you increase the current in opposite direction by decreasing resistance, the magnetic flux density starts decreasing and H starts increasing in negative area. So this is minus H. H starts increasing in a negative uh, value and B starts decreasing, and it will follow CD path, this CD. At D, at point D on the graph, what is happening? At point D, the B value is 0, but H is having some negative value. And this magnetizing force is known as coercive force. So the negative coercive force is the magnetizing force or magnetizing strength which is required to make the residual magnetism 0. If we still increase the magnetizing force in negative direction, magnetic flux density will be set up in opposite direction. So it will follow this path from D to E, and this E is negative saturation like positive saturation. Now in negative direction the saturation will be attained, and this value of maximum value of flux density is called minus B max. This is called minus B max. So at minus B max, it is the point of saturation. Beyond this point E, if we keep increasing current and if we keep increasing magnetizing force, magnetic flux density or magnetic flux density B will not be increased. It remains same. Again, after reaching point E, if we start increasing resistance, current will start decreasing. When current reduces, H will be reducing, and when H is reducing, it will reduce the magnetic flux density. Now it will follow the path EF. You can see here at point F, what is the situation? The situation or condition is at point F, the value of current and value of H are 0 here. But magnetic flux density B is not 0. It is having some negative value. So this is known as residual magnetism in negative direction. In earlier, this AC component is residual magnetism positive. This AF is residual magnetism negative. Now after reaching this point, again we need to change the terminals of the source as original connection, and once again we start decreasing resistance to increase the current. When current increases, H will be increased, and when H increases, it will increase the B. So it will follow FG path. At point Z, at point Z, B is 0 and H is having some positive value. So this AG component is known as coercive force positive, and positive coercive force is required to nullify the negative flux density to 0, to make the negative flux density 0. And after reaching point Z, if we still keep increasing value of current, the BH curve will follow GB path. So starting from A to B, B to C, CD, DE, EF, FG and GB. This is a cycle. This is a cycle. And once this cycle is completed, we will get this type of loop or graph, and which is known as BH characteristic, or it is also known as BH loop. This is also known as hysteresis loop or hysteresis curve. Why hysteresis? Here the meaning of hysteresis is lags behind. B lags behind H. At every point B lags behind H, and that is why it is known as hysteresis loop. So whatever I have narrated, it is written here. You just go through the content, read the process. As I said earlier, this point is the point where H value is 0 but B is having some positive value. This is called residual magnetism, and it is the property, and it is known as the remanence of the circuit. Remanence means a measure of the remaining magnetization when the driving field or driving force H is dropped to 0. Here this is a negative remanence. On this side it is the negative remanence. Coercive force or coercivity, it is a property of material which is required to drive the magnetization or magnetic field density to 0 after being saturated. So you can see at positive saturation the particles are aligned in this right hand side. With negative saturation, particles are aligned on left hand side. So it is completely two opposite phenomena. Now so just go through the content. In this diagram, whatever we discussed earlier is summarized, starting from origin to positive saturation, then remanence, coercive force, then negative saturation, then negative remanence, negative coercive force, and so on. So the material is magnetized to saturation in one direction at this point, and the material is magnetized to negative saturation at this side. Now if we calculate the area under the loop, then the area under the loop represents energy lost during this process. Which process? Reversal process. When we start increasing current in one direction, the particles are aligned in positive direction. For example, when we reverse the current direction, the same particles are aligned in negative. So from positive alignment to negative alignment, the particles change their position, and during this position changing, they lost the energy, and this energy can be calculated by calculating the area of hysteresis loop. And this energy lost is nothing but energy appears as heat in magnetic core, and it is known as the hysteresis loss. The equation for hysteresis loss is given as WH is equal to eta B max raised to n F into V, where this WH is hysteresis loss in watt, eta is Steinmetz coefficient, joule per meter cube, and its value depends on magnetic material. B max is magnetic flux density Weber per meter square, n is Steinmetz exponent, and it ranges from 1.5 to 2.5, depending on the materials. F is the frequency of flux reversal in hertz. So how frequently we are reversing the flux from positive to negative, negative to positive, and vice versa. And V is volume of the magnetic material. Please remember, V is not voltage, but it is the volume of magnetic core, and it is given in meter cube. The energy loss, this hysteresis energy loss associated with hysteresis loop, is directly proportional to area of hysteresis loop. For example, for hard materials, the hysteresis loop area is large, and because of that the hysteresis loss is more. For soft materials, the example of hard materials are iron, nickel, aluminum alloy, copper, nickel, cobalt alloy. For soft materials, the hysteresis loop area is narrow, smaller, and because of that the hysteresis loss is less. The examples of soft materials are iron, silicon alloy, ferrite, ferrous nickel alloy, and so on. So to design an electrical machine core, it is obvious that we have to select a material which is having less amount of hysteresis loss, and for that we need to select soft materials like iron, silicon alloy, ferrite, ferrous, nickel. So the two things are shown here. Large area, it means high energy loss, and small area, it means low or less energy. So three different types of areas are shown here, and obviously we can understand that in this types of material the maximum hysteresis loss WH will occur. This is intermediate, and in the last one, as the area is very small, the BS curve is very narrow, here there will be minimum amount of hysteresis loss. So this is the desirable characteristic for transformer, motor, and generator core to minimize the energy dissipation with alternating field associated with AC electrical applications. So in the next session, we will discuss static electrical machines, that is transformer.